In our previous video, we talked about systems of linear equations, and one of the most important results of this video is going to be relating this system of linear equations to this vector equation. You can see how we derive this vector equation from this system of equations when you realize the coefficients for x1 is our first vector and the coefficients for x2 is our second vector. And by this result here, these two, the system of linear equations and the vector equations, will have the same solution set. But before we get into this, we will first investigate or talk about vectors in general. Once we've gotten to the vectors and through this result, we will follow up with two other important concepts of vectors, and that is of linear combinations and span. In this video, we talk about vector equations. We start with the definition of a vector, which is a matrix with only one column. We have examples of R2, which is a set of all vectors with two entries in R2. This R stands for real numbers, so it's two real numbers, one column, two entries. And then we can think of vectors as ordered pairs of real numbers. So this vector 3, -1, we can also write that as the ordered pair 3, -1. And because it is an ordered pair, this is not equal to -1, 3, which would be the column vector -1, 3. Next, we'll look at vector addition. So if we multiply this vector x1, y1 plus x2, y2, we just multiply coordinate by coordinate. So that'll be x1 plus x2 and y1 plus y2. We will also look at this geometric interpretation of vector addition that uses the Parallelogram Law. We will look at vector multiplication, in particular multiplying a scalar times a vector. So if a is a scalar, in other words, a is a real number, then when we multiply it times a vector, we just multiply each coordinate by the scalar. And what we see is geometrically, our resulting vector points in the same direction, but is just scaled by a factor of a. Next, we have multiplication of a vector by a scalar. So if we have a scalar a, that is a is a real number, and we multiply it times a vector xy, we just multiply a times each coordinate. So we get ax, and then we have ay. Geometrically, what happens is the resulting vector points in the same direction as our original vector, but the resulting vector is scaled by a factor of a. As you can see, our first examples were in R2 because that's easier to graph. We also look at graphing R3, and then later we'll look at representing Rn. Next, we'll look at algebraic properties of Rn. So I'm just going to tell you also, as a matter of convention, vectors u, v, w, those will be typed in bold, whereas our scalars like c and d will be typed in non-bold. Also, when I write vectors, I'll try to remember to put the little arrow on top to designate vectors so you can see the difference between that and scalars. Our properties are that vector addition is commutative, it's associative, there's a zero vector, there are additive inverses, there's this distributive property of scalars times vectors, also of scalars added together times a vector, and then you can also have this associative property where you can group scalars before multiplying by vectors. Finally, we have the scalar 1 times a vector u, it just gives you back u. Whereas these definitions and topics are probably familiar to you, linear combinations may be new to you. So if you have p vectors in Rn, let's just call them v1, v2 up to vp, then you can multiply each vector by a scalar. We'll call those scalars c1, c2 up to cp. We can also call them weights. We multiply all the vectors by these scalars, and then we add these vectors together, and we get a new vector y. So y is called a linear combination of our vectors v1, v2 up to vp. And this is a very important definition for you to know, not just kind of understand, but actually to know and be able to write it out. And there's a very important linkage between linear combinations. So if B is a linear combination of the vectors a1, a2 up to an, there's an important connection or link with the augmented matrix here, where a1, so this represents a whole vector, a2 is a whole vector, so this is a matrix that's being represented, and that the connection is that B is a linear combination of a1, a2, an, if and only if there's a solution to the linear system corresponding to this matrix. The last topic we will cover is of span. So if we have p vectors in Rn, then the set of all linear combinations of those vectors is denoted the span of v1, v2 up to vp. And this is another important definition that you want to have memorized, not just sort of intuitively understand, although in the intuitive understanding we will talk about and hopefully will be really helpful. Another way of expressing this definition is that the span of these p vectors is the collection of all vectors that can be written as a linear combination of those vectors. That completes our 5-minute overview. This might have gone to 6 minutes. So now we'll go through each topic in more detail and with more examples. We'll back up and talk about a vector, and a vector is a matrix with only one column. In particular, we'll start with R2. That's the easiest to visualize, and that is the set of all vectors with 2 entries. So here is one example. U, the vector u is equal to 3 minus 1. We have another example, v is equal to 0.2 and 0.3, whereas w could be equal to w1, w2, where w1 and w2 are both real numbers. And the vectors are ordered pairs of real numbers, so 3 minus 1 can also be represented as the ordered pair 3 minus 1. And since it's an ordered pair, that is not equal to negative 1, 3, which means and negative 1, 3 is the vector negative 1, 3, but these two vectors are not equal since the order is not right. Also, just to note, 3, 1 is a 1 by 2 matrix. Remember, this is the number of rows, this is the number of columns. 1 row, 2 columns. And that is not equal to 3, 1, which is the 2 by 1 matrix. 2 rows, this is 2 rows, 1 column. If it helps you, you can think of these matrices as representing systems of equations. So this would be 1 equation with 2 unknowns, whereas this could be 2 equations with 1 unknown each equation. Next, we'll look at vector addition. We're going to illustrate this in R2, but the ideas extend to Rn. So if we wanted to add 2 vectors, what we do is just add the coordinates, the corresponding coordinates together. So we add the first coordinates together and then the second coordinates together. For example, if we want to add 2, 4 with 3, 1, we add the 2 and 3 together to make our new first coordinate, which is 5, and we add the 4 and 1 together to make our new second coordinate, also 5. Geometrically, we use the parallelogram law. So for this example, 2, 4 plus 3, 1, I have 2, 4 graphed here and 3, 1 graphed here. I'm going to take my vector 3, 1 and move it so the tail of this vector is at, or the beginning of this vector is at the end of my 2, 4 vector. Similarly, I'm going to take my vector 2, 4 and move the end of the 2, 4 vector so that it's at the beginning of the 2, 4 vector, so it's at the end of the 3, 1 vector. And now I have a parallelogram. I draw the vector then from the origin to the other corner of the parallelogram, and this gives me exactly the point 5, 5, which is exactly what I got when I did this algebraically. For subtraction, it's not hard to see that 1, 3 minus 2, 1 is going to be the 1 minus 2, and then the 3 minus 1, which is negative 1, 2. But what do we do graphically? We start with the fact that minus a has the same magnitude as a, but points in the opposite direction. So if a is equal to 2, 1 here, then minus a is going to be negative 2 minus 1, and we have that graphed here, and we can see same magnitude, opposite direction. And now we can add b to minus a, or b minus a. So I'm going to move my a vector so that its beginning is at the end of b, and then I'm going to move my b vector so its beginning is at the end of minus a, and I get my parallelogram. So the next, I can draw a line from the origin to the tip of my parallelogram, and this will give me the vector negative 1, 2, so negative 1, 2, which is exactly what I got algebraically. Next, we have vector multiplication, in particular a scalar multiplied by a vector. In this class, we're not going to do vector times vector, no dot products, no cross products. So if we have a, which is a scalar, so it's a real number, times xy, the vector xy, then we multiply a times every coordinate in the vector. So that would be a times x and a times y. So for example, and the geometric interpretation is that our resulting vector a, x, y, z points in the same direction as x, y, z, our original vector, but is scaled by a factor of a. So for example, if our vector is equal to 2, 0, which I have graphed here, it's 0 in the y-axis, but 2 along the x-axis. So this is our original a. If we multiply now by 2, that's 2 times a, which is 2, 0, which is 2 times 2, and 2 times 0, which is 4 times 0. So we have this vector here for 0, which is in the same direction as a, in the positive x direction, but twice as long. Whereas if we have 1/2 a, that's 1/2 2, 0, which is 1/2 times 2 and 1/2 times 0, which is equal to 1, 0. Again, we're in the positive x direction, but we're half the length of our original vector a. An example problem is let the vector u be 1, -2, and the vector v be 2, -5. We want to find 4u minus 3v, and then 4u plus minus 3v. Algebraically, 4u is just 4 times our vector 1, -2, which is 4 times 1, and 4 times -2, which is 4, -8. So I have graphed this here. I have my u, which is 1, -2, and then my 4u, which is 4, -8. So same direction, 4 times as long. Over here, I have my, where is it that I wanted to find? Minus 3v. So I have minus 3 times v, which is 2 minus 5. So that's minus 3 times 2, minus 3 times minus 5, which gives me -6, 15. So here I've graphed my original v, which is 2, -5, and then I graph my -3v, which is 6 minus 15. So you can see they're in opposite directions. They should be on the same line if I had drawn it well. Opposite directions, and this should be 3 times as long as the original vector v. I've gotten rid of my drawings to make room for my 4u plus minus 3v. So my 4u is 2 minus 8, and my minus 3v is minus 6, 15. So 4 plus minus 6, and 8 plus 15, or minus 8 plus 15 will give me my minus 2 and 7. Our next example, we have the vector u equals 2, 2, and v is equal to minus 6, 1. So we're going to add u plus v. So that's 2, 2 plus minus 6, 1. That's 2 minus 6 is minus 4, and 2 plus 1 is 3. Here is my graph. My u is 2, 2, and my v is minus 6, 1. To graph this, first I'm going to take my v vector, and I'm going to move the end of it, or the beginning of it, to the end of my u vector, and then I'm going to take my u vector, and I'm going to move the beginning of it at the end of my v. And now I can draw my line from the origin to the tip of my parallelogram, and I see now I'm at -1, 2, 3, 4, so minus 4, and I'm at 1, 2, 3, which is minus 4, 3, which is exactly the answer I got algebraically. Our next example, let the vector u equals 3, -1. We want to display u, 2u, and -2/3 u on a graph. We will start by calculating 2u and minus 2/3 u algebraically. So 2u is 2 times 3, -1, which is 2 times 3, which is 6, 2 times -1, which is -2. Minus 2/3 u is minus 2/3 times 3, -1, which is 2/3, -2/3 times 3, and -2/3 times -1, which is -2 and positive 2/3. Here I have u equals 3 minus 1 on my graph. To do 2u, it should be in the same direction but twice as long. So I have that graphed here, and that, as you can see, will be at my point 6 minus 2. Now for my -2/3 u, I want it to be 2/3 as long and in the opposite direction. So actually, let me just start by graphing negative u. So here I have negative u, kind of the same direction but in the opposite, same length in the opposite direction. And now I can take 2/3 of this. So taking 2/3 of this line will put me it'll actually put me at -2 and positive 2/3 here. I decided to make my negative 2/3 u in green here just so it differentiates from the blue. Now that we've gone over vectors, vector addition, and vector multiplication, we can talk about vectors in R3. Before we go into R3, I just have this statement that vectors start at the origin and they have magnitude and direction. Later, if we want, once we have the magnitude and direction of a vector, we can move it around, as we have been doing when we do vector addition. Anyway, going back to representing vectors in R3, we generally draw an x, y, and z axis this way, so x goes out, y goes to the right, and z goes up. And so if we wanted the point 2, 4, 4, we go along the x-axis 2 units. Then parallel to the y-axis, we go along y equals 4. And we're kind of imagining for y that these lines for y equals 1, y equals 2, y equals 3, and y equals 4, they run parallel to the x-axis. So here we'd have y equals 4. So this is our point 2, 4, where z is equal to 0. And now we need to go up 4 units. Roughly, this is about the space of 1 unit. So from here we go up 4 units, 1, 2, 3, 4. And so this would be our point 2, 4, 4. I'm going to do this again in more detail. For some reason, I changed the coordinates to 2, 3, 4. Just ignore the fact that we did 2, 4, 4 here. We're going to do 2, 3, 4 here. So we go along the axis 2 units, and you're just going to estimate that 2 units. You go along the y-axis 3 units, and then remember, when you draw, you're going to think of the y and the axis, this line here, being parallel to the x-axis, and then this line here is going to be parallel to the y-axis. So this is your point 2, 3, 0. Now from here, to get the 4, you don't just go up to z equals 4. This is down in the xy plane. You go up approximately 4 units using whatever scale you have for z. So this would be 1, 2, 3, 4. So to give you an idea of what this looks like dimensionally, so around my vector 2, 3, 4, I drew in this box to show you. So at the corner of this box, I have this plane here, which is at x equals 2. I have this plane here, which is at y equals 3. And I have this plane here, which is at z equals 4. And then, of course, the bottom of the box, where this point, the 0, 0, 0 is, I have the plane z equals 0. I have the plane y equals 0. And I have the plane x equals 0. And at this corner of the box, I have my point 2, 3, 4. And as we transition into Rn, I'm just going to say this 2, 3, 4 can also be represented as this column vector 2, 3, 4. So looking at vectors in Rn, I'm not going to draw those, and probably no one's going to ask you to draw them either when n is greater than 3. But the idea is you can extend all your addition, your multiplication operations algebraically into Rn. So it's represented as a column vector with n elements, or as an n-tuple, an ordered n-tuple. There's also something called the zero vector, which we'll draw with a 0 and a little vector sign above it, and that's just where all the elements are 0. Now we can talk about algebraic properties of Rn. So if u, v, and w are vectors in Rn, and they're all in bold, the scalars c and d, those are real numbers, then first we have that the addition is commutative. In other words, u plus v is equal to v plus u. Probably no surprise. We'll do a proof of this one in a minute. 2, we have this associativity, so it doesn't matter if you add u plus v first and then w, or you can add v plus w first and then add u. We have this additive identity, the zero vector. So the zero vector added to any vector, random vector u, just gives you back u. We also have something called an additive inverse. So u plus minus u, multiplying u by a negative, will give you the additive inverse that when you add it together with u, you get the zero vector. We also have this distributive property for scalars. So c times u plus v is equal to cu plus cv. And we have c plus d scalars times u is equal to cu plus du. Also, if we have two scalars, c and d, we can multiply d times u and then c, or we can multiply the scalars together first and then multiply by u. And last, we have this multiplicative identity, the 1 vector. So 1 times, or this is actually the scalar 1, I'm sorry, 1 times u is equal to u. The proof of these properties often rely on the properties of real numbers, but you need to get your vectors down to real numbers. So I will do this first property here, the commutativity, as an example. So I'm going to prove that the vector u plus v is equal to the vector v plus u in R2. And so u, I'm going to let that be u1, u2, and v equals v1, v2. So again, I'm kind of getting things down to the real numbers. Then one thing I like to do is a 2-column proof when possible. I do my steps on the left and I do my justifications on the right. So you'll notice whenever I do a proof for you, I will try to follow that format. So when I do u plus v, I'm going to substitute my u1, u2 plus v1, v2. And then by definition of vector addition, that will be equal to u1 plus v1, u2 plus v2. Now you notice here, I have real numbers, so I can use the commutativity of real number addition, so I can swap this to v1 plus u1 and v2 plus u2. Then, again, using the definition of vector addition, that's v1, v2 plus u1, u2. I just kind of use the other side of the vector addition, which is equal to the vector v plus vector u. And again, this is key to probably a lot of these. You're going to put everything in terms of real numbers over here, and then you can use the properties of real numbers to get you your results. And the other thing again is to notice kind of this 2-column proof technique where after you do a step, you're going to justify it. Next, we'll look at the definition of linear combinations. Given p vectors, so that's v1, v2, up to vp in Rn, so each of these vectors has dimensions n, and we have p scalars now, one scalar to multiply each vector, so c1 times v1, c2 times v2 up to cp times vp, so it's p vectors multiplied by scalars, then we add them together. That's equal to a vector y. That will give us a vector y, which we'll call a linear combination of the vectors. And the c's we'll call weights, and c's can equal to 0 as well. Think of linear combinations. I like to visualize my vectors almost like tinker toys. So I have a set of p vectors or tinker toys, and I have ways, I have methods of basically shrinking or expanding these vectors. They do, my tinker toys, they're fixed in what direction they point. So they're kind of a strange set of tinker toys. So, but I can expand with these scalars, or I can shrink them with these scalars, each of my tinker toys, and then I can combine them with this other special connector that happens to be vector addition. But the idea is that I have these tinker toys and I can expand, contract them, and then I can combine them to create new vectors, new tinker toys. And so to me, what linear combinations are is it's a way of taking a set of vectors and creating new ones. I have 3 examples here which I rewrote here. I could say y is equal to the square root of 3v1 plus v2. So y is a linear combination of v1 and v2 with weights c1 equals square root of 3 and c2 equals 1, or coefficient c2 is equal to 1. I also have y is equal to 1/2 v1, and so y is still a linear combination of v1 and v2 because remember, the coefficients or the weights can also equal to 0. So c1 is equal to 1/2 and c2 is equal to 0. Finally, y is equal to the 0 vector is a linear combination of v1, v2 because I can use c1 equals 0 and c2 equals c2 equals 0. And from this example, I will also mention that the 0 vector is a linear combination of any set of vectors because you can always choose the weights to equal to 0. And that solution is what we call the trivial solution, not because it's not important, but because everything is equal to 0. And by everything, I mean all the constants, all the weights are equal to 0. Here we have the vector v1 is equal to negative 1, 1, and the vector v2 is equal to 2, 1. And I wrote a bunch of linear combinations. So I wrote negative 1, 1 is a linear combination of v1 and v2 because that's equal to 1 times v1 plus 0 times v2. Negative 1, 2 is a linear combination of v1, v2 because it's equal to 1 times v1 plus 1 times v2. 1, 5 is a linear combination of v1, v2 because that's equal to 3 times v1 plus 2 times v2. And then 0, 3 halves is a linear combination because that's equal to 1 times v1 and 1 half times v2. And then finally 0, 0, as I said, the 0 vector is always a linear combination because you just multiply every vector by 0. So these are all linear combinations of v1, v2. Using these two same examples, v1 is equal to negative 1, 1, and v2 is equal to 2, 1, estimate the linear combinations of v1 and v2 that generate u and w in this picture. And the sets of parallel grid lines, these are drawn through the integer multiples of v1 and v2. So this diagram looked really busy to me the first time I looked at it. So first, let's look at it without all the other little extra lines here. I have drawn v1, which is negative 1, 1, and v2, which is 2, 1. So here's my v1, here's my v2, here's my w and u. So what we want to know is how can we scale these two vectors, possibly with negative numbers. Actually, we need to go negative, right, to get to this negative u. How can we scale these two so that we can get the vectors u and v? So the idea is somehow I want to scale v1, and then I want to scale v2. So let me start with v1. So I'm just going to extend it. Now, if I extend v2 in the positive direction, whatever I add then, if I add v1 and v2, I'm going to get stuff over here. So I can't reach w that way. But if I scale v2 in the negative direction, let me see, I want to try to scale this nicely, in the negative direction this way, then maybe I can get w by scaling v something like this. So maybe v1 gets 2.5 or 3, and v2, maybe if v2 goes to here, maybe it gets halved. Maybe that would give me w. But let me look at the lines that the book had given me on this problem. Well, your book had talked about the set of parallel grid lines are drawn through the integer multiples of v1 and v2. So let's look at, first I'm just going to scale v2 in the negative direction and v1 in the negative direction. And then I'm going to look at integer multiples. So if this is v2, this is going to be twice v2. This over here is going to be 3 times v2. In the negative direction, I have my negative v2 and my negative v3 vector will end over here. Okay, so I didn't draw the lines. Here I have my v1, so 2v1 will end here, and 3v1 will end here, whereas negative v1 will be here, negative 2v1 will be here, and negative 3v1 will end here. So let's just look. I'm going to draw a line through the integer multiples of v1, and I'm going to draw a line through the integer multiples of v2. So these are the lines when I add v2 to negative v1 or negative integer multiples of v1, I can get these points over here. Over here, I can get the points between when I have positive v1 and I add that to positive v2, I get these points. When I add positive v1 to negative v2, I get the points in here. And when I add negative v2 and negative v1, I get the points in here. So for example, let's just start by adding v2 to, say, example, negative v1. So I have v2 added to negative v1. Using my parallelogram law, I would draw the parallelogram, and here would be my resulting vector, negative 2v1 plus v2. So that's what these lines are for. It's for adding the different multiples together. And as I said, here's my v2 line, here's my negative v1 line. So in this area here, which I'll just kind of shade in yellow for now, this is where I can get points where I add things in the positive v2 line and the negative v1 line. Now, for example, I can do v1 minus v2. So here's my line of my v1 multiples, my v2 multiples. If I use v1, the multiple is just 1, v2, the multiple is -1, I do my parallelogram law, and I get this point here, v1 minus v2. And as I had mentioned before, as I look along the positive v1 axis and the negative v2 axis, I can get these points in this yellow shaded region. And now I've added the other grid lines for different multiples. So like here, I can add something like 2v1 and v2, and I get this point. So the positive v1 line and the positive v2 lines give me this area. The negative v1 and negative v1 and negative v2 gives me this area here. So now I want to know approximately, let's look at u first, approximately where does u lie? So it looks like it's somewhere around 3v1 and negative 2v2, right? If we draw the line 3v1 and 2v2, doing the parallelogram law, we would get u. So I'm going to write that u is equal to 3v1 minus 2v2. So this is my solution. U is a linear combination of v1 and v2 with weights 3 and -2, or coefficients 3 and -2. Looking at w, so this one, it's not too, it goes in the fractions, but here I am at v1. I need to get up somewhere a little more than 2v1, between v1 and v3. And over here, I need to get maybe halfway over to -v2. And it ends up, this is going to be, w is equal to 5 halves, so halfway between 2v1 and 3v1, minus 1/2 v2. So this is my final answer. W is also a linear combination of v1, v2 with coefficients or weights of 5 halves and -1/2. My next example, let A equal the vector 1, -2, 5, and A2 be the vector 2, 5, and 6, and B be the vector 7, 4, -3. Determine that the vector B can be written as a linear combination of vectors A1 and A2. That is, determine if there exist weights x1 and x2 such that x1 A1, vector A1, plus x2, vector A2 equals vector B. So I wrote that out. My x1, my first coefficient, times my vector a1, 1, -2, 5, plus x2 times my vector a2, which is 2, 5, 6, equals my vector b, which is 7, 4, -3. So we're looking to see if b is a linear combination of the vectors 1, -2, 5, and 2, 5, 6. Writing this out, I can multiply my scalar x times my vector, so I get x1 minus 2x1 and minus 5x1. I can multiply x2 times my vector 2, 5, 6 and get 2, x2, 5, x2, and 6, x2 equals 7, 4, 3. But this is just equal to the linear combinations, or the system of linear equations. X1 plus 2x2 equals 7, minus 2x1 plus 5x2 equals 4, and minus 5x1 plus 6x2 equals -3. So this is important to be able to see this linear combination of vectors, also see that it is equivalent to the system of equations. This is a very key step right here. And the reason why it's so important is because we know how to solve these. We can use our matrix, our augmented matrix, 1, 2, 7, -2, 5, 4, and -5, 6, -3. And we can do elementary row reductions until we get the equivalent echelon matrix of 1, 2, 7, 0, 1, 2, and 0, 0, 0. I did one more step to get the reduced echelon form. So I have 1, 0, 3, 0, 1, 2, and 0, 0, 0. I wrote x1 and x2 underneath because this column is associated with the the first vector, and x2, this is associated with the second column vector. So I had the equations. I have 0 equals 0. That's great. x2 is equal to 2, and x3 is equal to 3. So this is my linear combination. In other words, my 3 times my first vector, 1, negative 2, 5, plus 2 times my second vector, 2, 5, 6, should be equal to, well, I'm going to calculate it. That's 3 plus 4. This is negative 6 plus 10, 2 times 5. My minus 15 plus 12, so this is 7, 4, negative 3, which is exactly my vector b. So b can be written as a linear combination of a1 and a2 with x1 equals 3 and x2 equals 2. And this example was an illustration of this statement here. A vector equation x1 a1 plus x2 a2 up to xn an equals b. So that's this equation here. We have our x1 and then a1 is equal to 1, negative 2, 5. Our x2 and our a2 is equal to 2, 5, 6. And our b is equal to 7, negative 4, 3. It has the same solution set as the linear system with augmented matrix a1, a2, and b. And remember, this a1 is the entire column vector, so a1. So this linear equation has the same solution as the linear system as the augmented matrix, which we used and I got rid of. So I squeezed it in here as this augmented matrix, 1, 2, negative 5, 2, 5, 6, 7, 4, 3. So it has the same, this is my A1, my A2, and my B matrix. So it has the same solution. Remember, we found the solution to this matrix to be 2, 3, and that was the same as our linear combination. In particular, B can be generated by a linear combination of our vectors A1, A2, AN, if and only if there exists a solution to the corresponding matrix. And that's exactly what we did here in this problem. And again, it's because the key was this linear combination of vectors, this linear combination problem was equivalent to the system of linear equations. And I cleared out some of the things so I could explicitly write this. This linear combination of vectors, this vector equation, is equivalent to the system of linear equations. And remember, this vector here in front of x1 are the coefficients in front of x1 in our system of linear equations. The second vector in front of x2 is our set of coefficients in front of x2 in our system of linear equations. And then our solution, our b vector, are equal in both cases. And this equivalence is what I had mentioned at the beginning of our video, is one of the main results of this video. And that statement was this statement here, the same statement. This is in our overview slide, just so you know where it is, with an asterisk, because it's one of the key ideas that we want. Moving on, our last topic is that of span, another key, very important idea. You do need to memorize the definition of linear combination. Don't just know or understand about it and kind of be able to work with it. You actually need to be able to, if someone asks you, be able to write down the definition. Span, same thing, be able to write down the definition. And the definition is, if you have p vectors, v1, v2 up to vp in Rn, then the set of all linear combinations of the p vectors is denoted span of v1, v2 up to vp. So the span is the set of all linear combinations of the vectors. That's the definition you want to memorize. And it's called the subset of Rn spanned by the vectors. That is, span is the collection of all vectors that can be written in the form, and we have this linear combination formula where v1, v2 up to vp, they're all multiplied by different constants or potentially different constants, maybe they're all the same, and then they're added together. And now I'm going to double down on my Tinker Toy analogy, the one where I consider my vectors as these strange Tinker Toys that always, you have these little arrows that always point in the same direction, but you can combine them by shrinking or contracting them. Also, you can multiply by negative scalars, so you can make them reverse direction, and then you have this other connector thing that then allows you to connect them with the rules of vector addition. So you're creating these new vectors, and what the span tells you is what vectors you can create from your set. So in other words, if all of my vectors happen to point to the right, I can contract and I can extend them, I can point them the other direction, and then I can combine them, I can add them together, I can get all kinds of vectors pointing to the right, all lengths of vectors pointing to the left, but there's no way that I'm going to be able to get a vector that points upwards. In other words, The span tells me, given a set of vectors, what other vectors can I create through linear combination with my original set. We have two more comments asking if B is in the span, amounts to asking whether the vector equation x1v1 plus x2v2 plus xnvp has a solution. Oh, this should be equals B, has a solution, or equivalently whether the linear system with augmented matrix has a solution. And then second, we want to note that the span of p vectors contains every scalar multiple of v1, and also that the zero vector is equal to zv1 plus z0v2 plus 0vp. And just to be really explicit, why does the span of v1 through vp contain every scalar multiple of v1? Well, because y, that's all of our linear combinations, can be set to be equal to c1 v1 plus all the other weights can be equal to 0. So as long as c1 can be any constant, that means we can always write any scalar multiple of v1 as a linear combination of our p vectors. So our first example, the span of a single vector is a line. So let's say we have a vector v that I've drawn here, and then we want to consider all the span of v. So that would be all the constant c1 times v. That's essentially the span, all the linear combinations of v. There's nothing else to add to it, but we can scale it. So what that means is when we multiply by positive scalars, if it's a fraction, you get a fraction, half of the vector, or a fraction of the vector. When it's positive and it's greater than 1, we're going to extend v out positively. When c1 is negative, we're going to extend in the opposite direction. So you can see we get this line. A single line would represent c1 times v. Our next example is the span of two linearly independent vectors is a plane. And by linearly independent, I mean they're not just scalar multiples of each other. In other words, not just the same line, just multiplied by some scalar. So I'm going to use this drawing here to illustrate if I have a vector u and a vector v, it will span the entire plane. And if we're in 3 space and we have two vectors, the illustration is, or the argument is the same. I'm going to extend u by all the scalar multiples of u. Again, that would be a line. And I'm going to extend v by all the scalar multiples of v. So I'll start, if I scale my u by something like, 1/2, and v by some other fraction, let's just say this is 3/4. By my parallelogram, I take this vector, I move it to the tip of the other vector, I take this vector and I move it to the tip, and I'm going to get this point here. And if I just add u and v together, if I take twice u and twice v, then I use my parallelogram law, and I'm going to get this point out here. So far I have everything along this line. If I wanted to get something off this line, but within these two vectors, I could do something like 1/2 v and twice u. So let's do 1/2 v twice u. So moving my 1/2 v, moving my twice u, I get this point over here. I can do something like twice v and 3/4 u, and I might get, let's see, moving my twice v, moving my 3/4 u, I'll get something not quite on the line. It looks a lot like it's on the line, but it's not quite on the line. But the idea is by taking positive weights for u and positive weights for v, I get these points in here in this region that I'm going to shade in yellow. You can do the same sort of thing. If you take negative v and negative u, you're going to get the points in this region here. But if you take positive u and negative v, you'll get this region in here. If you take positive v and negative u, you'll get this region down here. So by taking all the different combinations of u and v, you're going to get the entire plane. As I had mentioned, if you were in three-dimensional space with an x, y, and z coordinate, you still have u and v, which are two vectors. They're also in three-dimensional space, whatever their coordinates are. You know, your u plus v, you still end up with this plane in the three-dimensional space. Okay, so now I have a new example. Let a1, the vector a1 be 1, negative 2, 3. The vector a2 be 5, negative 13, negative 3. And the vector b equals negative 3, 8, 1. So the span of a1 and a2, as we know, is a plane through the origin in R3. And also, yeah, that it always contains the origin because the span always has the 0, 0 vector. And the question is b in the plane? Asking if b is in the plane spanned by a1 and a2 is the same thing as asking is b in the span, or is b a linear combination of a1 and a2? In other words, can we rewrite b as b equals x1 a1 plus x2 a2, where x1 and x2 are scalar coefficients? And I rewrote this again as x1 times our vector a1, which is 1, negative 2, 3, and x2 times our second vector, 5, negative 13, negative 3, equals b, negative 3, 8, and 1. And we're going to use that important transition that is that this vector equation here has the same solution as the linear system with augmented matrix, and I wrote the augmented matrix here. The a1 is 1, negative 2, 3, a2 is 5, negative 13, negative 3, and b is equal to negative 3, 8, and 1. So I moved this up so I'd have more space. I row reduced until I got 1, 0, 0. That's associated with x1. 5, negative 3, 0 associated with x2, and negative 3, 2, negative 1. And just looking at this last line, this means 0 times x2 is equal to negative 1. And there's no x2 that will satisfy this equation, meaning that this is an inconsistent set of linear equations. There's no solution. So b is not in the plane spanned by a1 and a2. I want to emphasize that the important part of this problem are rewriting what the problem statement is into this vector equation, and then understanding the vector equation, how it relates to this augmented matrix, and then getting no solution and being able to understand that it's not b. That means that b is not in the plane spanned by a1, a2. All these calculations here, you can put this in there's programs for that on the web to do the matrix reduction for you automatically. So it's not these row reductions, they really aren't that important. It's really how you get to interpret the question, how to write the correct linear equation, how to then interpret the solution. And the way you do all these correct interpretations is by being able to understand what it means to be in the span, what it is to be a linear combination, and then again, just interpreting it again, what it means to be in the span. Another example in your book, this is supposed to be an example of an application. A company manufactures two products. For $1 worth of product B, the company spends 45 cents on materials, 25 cents on labor, and 15 cents on overhead. For $1 worth on product C, the company spends 40 cents on materials, 30 cents in labor, and 15 cents on overhead. So let B be the vector 0.45, 0.25, and 0.15. That's the money spent on materials, labor, and overhead. And C be the vector 0.4, 0.3, and 1.5. Again, the money spent on materials, labor, and overhead. Then B and C represent the cost per dollar income for the two products. So it's the cost associated making $1 of income for the two products. A, what economic interpretation can be given to the vector 100B? And B, suppose the company wishes to manufacture X dollars worth of product B and X dollars worth of product C. Give a vector that describes the various costs the company will have for the material, labor, and overhead. For 100B, I have that this is 100 times the cost per dollar of income, which I got from the problem statement here that I'm circling. So the cost of producing $100 worth of product B, which is 100B is 100 times the 0.05, 0.045, 0.025, and 0.15, which is 45, 25, and 15, or $45 of material, $25 of labor, and $15 of overhead to produce $100 worth of product B. For part B, the company wishes to manufacture X dollars worth of product and X $2 worth of product C. Give a vector that describes the cost. Well, the B is the vector associated with the cost of product B. So if you want X dollars worth of product B, that would be X1 times B. And X $2 worth of product C will be X2 times the vector C, which is the cost per $1. I have two more problems to do. The first problem, prove U plus V equals V plus U, the vectors, that vector addition is commutative. We already did this earlier when talking about algebraic properties of Rn. The second problem, prove what values of H will Y be in the span of V1, V2, V3 if V1 is equal to 1, -1, -2, V2 is equal to 5, -4, -7, and V3 is equal to -3, 1, 0, and Y is equal to -4, 3, H. So Y is going to be in the span, by definition of span, if Y can be written as a linear combination of V1, V2, V3. So I wrote that here. Y is in the span of V1, V2, V3 if there exist scalars x1, x2, x3 such that Y equals x1, V1 plus x2, V2 plus x3, V3. In other words, Y is a linear combination. So I wrote Y then, which is minus 4, 3, and H is equal to x1 times V1, which is 1, -1, -2, x2, V2, which is 5, -4, -7, and x3, V3, which is -1, -3, 1, 0. And then that other key is to see that this vector equation has the same solution as this augmented matrix of A1, which is 1, -1, -2, A2, which is 5, -4, -7, and A3, which is -3, 1, 0, times B, which is -4, 3, H. So I work with row reducing with H just as some variable, and I get the reduced matrix of 1, 5, the echelon matrix of 1, 5, I should read down the columns, 1, 0, 0, 5, 1, 0, -3, -2, 0, and 4, 1, -5, H. And my first column is associated with x1, my second with x2, and my third with x3. So what this tells me is that 0 is equal to -5 plus H. And I also have that x2 minus x3 is equal to -1, this should be a -1, and x2 plus 5x2 minus x3 minus 3x3 is equal to -4. These two equations here with a minus over here. This over here tells me that, the first line tells me that H is equal to 5. I also have that, so what's free? My x2 is dependent, x3 is free, and x1 and x2 are dependent on x3. So you can choose whatever number you want for x3, that'll give you x1 and x2, but our H must equal to 5. This value here equals to 5, and that's from this last equation here. So that's your answer, that H will have to equal to 5. And the last problem is let W1, W2, W3, U, and V be vectors in Rn. Suppose that U and V are in the span of W1, W2, W3. So think about what that means. What's the definition of span, which I wrote up here. Show that U plus V is also in the span. And there's a hint, the solution requires the use of the definition of the span of a set of vectors. So here's my solution. So U and V are in the span of W1, W2, W3. What that means is that U and V can be written as a linear combination of W1, W2, and W3. So that's what I've done here. I've written U as a linear combination of W1, W2, W3, choosing A1, A2, A3 as my constants, my real numbers, my scalar, the weights, that's what it is that they call them here, or coefficients. Then also V, I did the same thing. I chose my coefficients B1, B2, B3. Those are my scalars, my weights. to multiply W1, W2, W3. So U and V are both linear combinations, can be expressed as a linear combination, W1, W2, W3, and that's just from the definition of span. So now I'm going to consider U plus V. So I write U plus V, so I wrote it out as a linear combination, U as a linear combination of W1, W2, W3, and V as a linear combination of W1, W2, W3. And I just substituted that from above because, again, U and V are in the span of W1, W2, W3. Then this is equal to, now A1, W1 is a vector, A2, W2 is a vector, A3, W3 is a vector, B1, W1 is a vector, B2, W2 is a vector, and B3, W3 is a vector. And since vector addition is both associative as well as commutative, I can rearrange these terms. So I can rearrange A1, W1 to be next to B1, W1, A2, W2 to be next to B2, W2, and A3 to be next to B3, W3. From our algebraic properties of vectors, this is property number 6, where we had two constants times a vector. We can then say that equals the constant times our vector plus our second constant times our vector. I then factor out my A1 and B1, so these are my two constants times a vector. So it has the same form. Similarly, I factored out A2, B2, and A3, B3. And now, since A1, B1, and A2 plus B2, and A3 plus B3 are all real numbers, these become my new weights. So then what that tells me is U plus V is equal to a constant, or a weight, or coefficient times W1, a weight times W2, a weight times W3. So therefore, U plus V is in the span of W1, W2, W3 from the definition of span. I want to give you one more example of span, and that is if we have A1 is equal to 1, 2, 0, A2 is equal to 1, 0, 1, and A3 is equal to 2, 2, 1, do the vectors A1, A2, A3, does the span of these vectors equal to the whole space, R3? In other words, to span R3, we're saying that every vector in R3 must be a linear combination of A1, A2, A3. So take a look at that. And then we're going to consider B, our vector B, a random vector B in R3, which will represent as B1, B2, B3. Can it be written as a linear combination of A1, A2, A3? In other words, is this random vector in the span of A1, A2, A3? And to solve this, we're solving this vector equation. Can B, B1, B2, B3, be written as a linear combination, x1 times our first A1 vector, x2 times our A2 vector, plus x3 times our A3 vector? Does this vector equation have solution? And so we look at the related system of equations here, where we take our first vector, our second vector, our third vector, and then our B vector. We row reduce it, and we get that 0 equals B3 plus 1/2 B2 minus B1. So that means in order to have solution, this relationship has to hold among B1, B2, B3. So this A1, A2, A3 only span if B1 is equal to B3 plus 1/2 B2. So A1, A2, A3 do not span the entire space of R3. A related question then is, what set of three vectors do span R3? And the easiest example, or the most canonical example would be 1, 0, 0, 0, 1, 0, and 0, 0, 1, because when we take a random vector in R3, let's call it B1, B2, B3, then our vector B can be expressed as a linear combination of 1, 0, 0, 0, 1, 0, and 0, 0, 1 using B1, B2, and B3 as our coefficients, or as our weights. To review what we've talked about in this video, we talked about vector equations first. We talked about vectors, which are one-column matrices. And we talked about R2, which is the set of all vectors with two entries in R2. So our examples were things like 3, -1. And we said that vectors can also be written as ordered pairs of real numbers. So for example, 3, -1 can be written as 3, -1. And since that's not equal to -1, 3, which is equal to the vector -1, 3, these two vectors are not the same. 3, -1 and -1, 3 are not the same vectors. We talked about vector addition, that when you have x1, y1 plus x2, y2, you just add the first two coordinates together, x1 plus x2, and then you add your second two coordinates together, y1, y2. And we had the interpretation, we use the parallelogram law. So if we were trying to add 3, 1 to 2, 4, we take 3, 1, and we translate that vector up so that its beginning is at the end of 2, 4. And actually the end of that vector will be 5, 5, which will be our sum. But we actually did the full parallelogram. So we took 2, 4, we translated the beginning of this vector over to the end of 3, 1, and we drew the parallelogram. We draw the vector going from 0, 0 to the tip of the parallelogram, and we get 5, 5, which is the same solution we would get if we did this algebraically, which is 3, 1 plus 2, 4. So 3 plus 2 is 5. 1 plus 4 is also 5. We talked about subtracting vectors. That means you just take the negative of your vector, one of your vectors, and then you add them together. We did vector multiplication, so we didn't do like dot product or cross product, but we did scalar multiplication. So if we have a, which is a real number, and we multiply it times a vector, that's just a times each of the coordinates. So we have ax, ay, and the geometric interpretation is your new vector points in the same direction, but is scaled by a factor of a. If it's negative, it points in the opposite direction. We talked about how to draw vectors in R3, and then we talked about representing vectors in Rn. It's just an n-dimensional, n rows, one column vector. We had algebraic properties for Rn. So if u, v, and w are vectors in Rn and c and d are scalars, then addition is commutative, and we did the proof of this one. It's associative. There's a zero vector. There's zero additive inverses. There's this distributive property of c times the addition of two vectors. There's this distributive property when we have c plus d times a vector. And we have this where we have multiple scalars multiplied by the vector. And then we also have the scalar 1 times u is equal to u. We talked about linear combinations. So given p vectors in Rn, then we can multiply each of the p vectors by a scalar, c1 through cp, add them together, and that'll give us a y, and we call y a linear combination. So a linear combination is you take the vectors, multiply it by scalars, then sum them up. And the scalars can be equal to 0. We had also this fact here that when we had a vector equation, when we write something as a linear b as a linear combination of vectors a1, a2 up to an, that this will have the same solution set, x1, x2 up to xn, as the linear system with the augmented matrix a1, a2, an, and b. Remember, this a1 is an entire column vector. This a2 is this column vector, and b is a column vector. And then finally, we talked about span. If we have p vectors in Rn, then the set of all linear combinations of those vectors is denoted the span. And these three definitions, I should say, these two definitions, linear combination and span, are really important that you're able to write down the definition exactly. It's not enough to just kind of get a feel for the definition. You want to know the definition. And then this, the vector equation, translating it to a matrix should be something that should come very naturally to you as well. So that's it for this video. Thank you for watching.